of the electron. So far, we've been focusing mostly on light. Now we're going to look a little bit more at electrons. So Bohr came up with his model of the atom. Why were those electrons restricted to orbiting the nucleus at certain fixed distances? Louis de Broglie, a French chemist, he reasoned that since we've been looking at light waves, they can also behave as particles. Well, maybe it's the same the other way around. Maybe particles like electrons can also have wave-like properties. So he proposed that the electrons orbit in wave patterns as standing waves. So the idea here is that we have to start and stop at the beginning and the end of the wave here. We can't have a wave that ends up above or not right at that point. So this is going to limit to the distance that our waves can be. If we turn this into a circle, like we picture the atoms, right? Here, we pick a point out of the wave. We go, that's 1, 2. So that right there is showing us that 3 waves, 4 waves, 5 waves, 6 waves. But we can't have something like this where they're not lined up. So we end up with certain distances then that we're allowed to have these energy levels with certain number of waves that we go through. He came up with this equation here where the left-hand side of the equation, we're looking at the electrons, or any matter actually, as waves, and on the right-hand side of the equation, we're looking at it as a particle. So it's kind of bringing together the idea that it's a wave and particles. We don't see it on the macroscopic scale just because the masses are so big at the macroscopic level compared to when we're down at the atomic level. 7.5, talking about quantum mechanics. Heisenberg came up with his uncertainty principle. Impossible to know simultaneously both the momentum, that's this rho or p, and the position of the particle x with certainty. There's a good video that was that we watched. Schrodinger, he wanted to look at it more mathematically. Can we predict where those electrons are, where that electron is? This worked really well for hydrogen, but it didn't work well for multi-electron systems. So it actually worked well for hydrogen, for a helium ion, if they stole 1 electron away. So again, it only had 1 electron. Or lithium with only 1 electron. So it worked well for those. It predicted where the electron would most likely be located, but not for when we had more than 1 electron. So we went from picturing where that electron is to now it's all about probability. It's where is it most likely to be. Schrodinger's equations describe the behaviors at the sub-microscopic, again at the atomic level, and just like Newton's laws did to macroscopic particles. Again, since the forces are like gravity, it's really important with big massive particles, but it's not important when we're talking about those sub-microscopic particles. And that's the big difference with the forces that are at play and which ones are most important. Schrodinger's equation works well for hydrogen, but not for more complex systems. We were able to use Schrodinger's equations to predict some of the shapes that we'll see later on of where the electrons, again, are most likely located. Okay. We can get the electron density. So what they could do is we could look at, say we had hydrogen, and we could fire X-rays at hydrogen, and we could get an idea by when the X-ray comes in contact with the electron, the X-ray is going to bounce off the electron, and by finding out where and with what force the X-rays came off, we can get an idea of where those electrons are. And we can get what's called an electron density map. And that's the probability of where that electron is most often. If we looked at hydrogen, it's a big sphere around the center of the nucleus. Exactly what we would picture when we're talking about a fuzzy electron cloud. As you get farther and farther away, there's less chance to see the electron out at those greater distances. So there is no clear-cut end to the atom, again, because it's just a probability of where those electrons are most likely to be located.